Okay, thanks for joining us for the Western Wheels Conference. A couple quick things before we begin. If you need a certificate, you'll find the link for that here. You'll need to submit a separate request for each session that you attend, and you should receive your certificate in email within 24 hours of submitting the request. If there are any handouts available, you'll find those there. And if you're interested in learning more about any of the products featured in our sessions, that'll take you to the product page for each one. And if you click request pricing, that'll add it to your wish list. Here we are at the wish list. You can either complete the form and submit it right away, or you can keep browsing around and adding items to it to get one big quote. And you can always get back to your wish list right up here in the top right-hand corner. That's it. I hope you enjoy the session, and we'll see you on the other side.
Well, good to be here, guys and gals. Maybe there's a few women. That would be nice. What I'm going to try to do is I'm not going to duplicate what Dick did, but I'm going to do some of the slightly different adaptations of that. In the process, I'm going to be using this baby back here. This is an EM330. You'll see a little later, you'll see the fascia plate on it because I've got another camera on that. But it has all the basic sensors, inputs and outputs for a fuel system, fuel injection up here, and an ignition system here. Now, what I'm trying to do today is spend some time on fuel and ignition with an emphasis toward some of the changes. So even though I've got a lot of material in my presentation, I'm going to probably wind up skipping over some of it on purpose. There are two handouts. There's an ignition handout and a fuel handout. And I assume that JB will take care of that when the time is right. And JB, I don't care when you want to do it. I won't say that this slide series or PowerPoint totally follows it, because I wrote the ignition and I wrote the fuel, I don't know, maybe a year or so ago. And then I did over the last week or so, I've done some adaptation here. So anyway, that's what we're going to try to do. And what I'd like to do now is switch over to the PowerPoint. I think the emphasis here is, what are we teaching, how and why? Now, I think everybody that you're going to see during this conference are teachers. You know, I taught for many, I won't tell you how many years, but I've been teaching. Well, I've been teaching a long time, and Dick has, and you know, and Tim Dwyer here, and Jeff Curtis. I mean, and Rick Martineau. We've got a lot of experience, so we know the issue that you have with time. And I frequently have guys that either send me a comment or they comment in a live class and say, you know, I don't have time to teach that. So I think what you have to do is economize your teaching in terms of determining how and why and what you're going to teach. So we'll take a look at that. So what are we going to do? Well, we'll take a brief look at the different types of systems. There are quite a few systems that are just not on the road anymore, and I'm going to ignore them. I'm going to walk you through something that I like to do with a beginning digital storage oscilloscope. That's easy for me to say, a digital storage oscilloscope class, or a class that's basic to basic in fuel or basic in ignition. We'll show you how to do that. We're going to download and analyze some voltage waveforms. Many of the waveforms are in my PowerPoint, so I don't have to necessarily download them, but we're also going to, you'll notice the last one on here is GDI. I'm going to spend quite a bit of time on gas direct injection because I believe that's what you should be doing. And of course, they offer some unique things. And we'll talk about current waveform patterns, and we'll look at fuel pumps, assuming we have time. My name's Al Santini. See, I won't tell you how long I've been teaching. I usually put up here, I'm older than dirt, but younger than Dick Krieger. But because it was his birthday, I thought, well, I'll be nice to the old man. I've
You didn't
written
say it,
some.
but you said it, Al.
Well,
Al, we're still looking at you, buddy.
Yeah, we're not seeing your screen yet.
well, what the hell? Okay, time out here. Sorry about that. Okay. I'm currently with ConsuLab as a technical trainer, and I assume most of you know that. I'm at home working on cars or on the water. That's me and my sailboat on the right there. Anyway, if you're trying to get a hold of me, and please feel free. I don't share my email with everybody on the internet or anything else, but I do obviously when I teach any of the classes. So Santini at ConsuLab.com, and that'll get to me, and that's important. Let's talk for a minute, and let's kind of pick up where Dick left off. With connections, you have to recognize that wherever you connect that ground, that is going to be 0 volts on your oscilloscope. So if you connect it to some rusty old crappy bolt that's been riding on this car for 150,000 miles in salt, and you know I'm from Northern Illinois, so we love salt. We just pour it on the roads, even when we don't need it. I think there's probably a salt truck out there right now just getting ready for next winter. So you know these connections have got to be good. The ultimate is obviously the battery. When you're dealing with any of the ConsuLab products, they bring a ground to you know a good ground out to everybody so that you can connect there and be in good shape. The other lead is going to be the signal. The signal is always based upon ground. Important. So that's why you need a good ground. Okay. These are becoming a little harder to get. They are in the handout, and maybe we can also put it in the chat. I'll put it in the chat later. Delco has these. They used to be called PD10s, and they're still making them, believe it or not. They're small, little, like a glorified Scotch locks, expensive Scotch locks, and you clamp it around a wire. It stays with the car. It slices the insulation, and then it insulates it with silicone, which is in the little Scotch locks, like I said. They're not cheap, but they save the car. And the nice thing about it is, I mean, I've got the luxury here today of having a breakout box. I have the luxury of you having a breakout box, and I know you might not have that luxury. But by the way, in the future, keep in mind one of the biggest advantages to any type of engine bench or something like that is the ability to be able to make these connections and not have to be disconnecting connectors. Because if you have students disconnecting connectors, you know you're going to have problems. Okay, this is an older oscilloscope, and I will flip between 3 or 4 different scopes just to try to get across the idea that you can do what we're going to talk about with anything, with almost any oscilloscope. Notice all the this is actually a DC. It's actually almost a low volt signal, and the signal is being impaired by wire routing. In other words, what I did to get this is I took my oscilloscope wires and I ran them right over the top of the alternator. I was actually touching the alternator. And then I turned on every accessory on the automobile. So I was producing massive magnetic fields. That magnetic field interfered with the signal. Okay. How do you make sure that you can eliminate this? One is ground. Make sure you have a good ground. If you see on the signal amplitude, and amplitude means that you have a signal either going up or going down. Okay. It doesn't have a time base though. I mean, I know these are kind of a little hard to see, but there's a good example right there. That's an up down with nothing else. There's a whole bunch of them here. These will make your reading very difficult because especially with students, because students look at it and they go, oh, why is there all that stuff on it? Well, you know, some of it is noise. You have to recognize that in the automotive shop, your shops, you have compressors, you have cars that are running with the hoods up. Okay, you have fluorescent lights. God only knows what else you have in the shop, but all of it generates RFI, radio frequency interference. and that interference can get into your oscilloscope. So use good quality leads, and if you break a lead, replace it. Don't keep using it, okay, because you're going to wind up with an issue, okay? I'm going to show you a little bit of the use of low pass. Now, what low pass filtration is, just what the name implies, low frequency passing. So it blocks high frequency, and it's adjustable on many oscilloscopes. And I'll show you, I'll talk a little bit about that. The current probe, Dick's already talked about it, but one of the things about it that's really important is when you talk about using a current probe, and this presentation is on ignition and fuel, bingo, that's where the current probe really belongs, okay? Set up using a probe. Now, what I mean by this is you will find some DSOs, let's say the Pico, for example. The Pico allows you to set the use of a current probe so that the screen actually shows you in amps or milliamps. Okay, that's not absolutely necessary, because if you look on the scale, okay, there's a couple of things that you can do. First of all, we need a green power light. We make sure the low battery light is off. Now, this is a Pico, and there are other current probes out there. Some of the current probes will blink the power when the voltage is getting low on the battery. Because remember, these are internal batteries, so they gotta have that. You gotta keep that in mind. Now, this one has two different scales. What does this really mean? Well, look up at the picture and see the 20 amp scale. You have in parentheses 100 millivolt / amp. What does that mean? It means if this current probe is clamped around a wire that has 1 amp flowing in it, clamped around a wire that has 1 amp in it, flowing through it, this will generate a 100 millivolt signal. So is it really necessary to set your DSO, or you have a DSO that doesn't have a current setting? Yeah, it does have a current setting indirectly, because we know if we put a clamp around it, we have 200 millivolts, and we're on this 20 amp scale. How many amps do we have? Well, let's see, 100 millivolts equals an amp. So 200 millivolts equals 2 amps. Easy, piece of cake. This is probably a simpler way than actually setting. Now, once your students get good with it and you show them, you say, well, okay, here's how we do this. You will also find that the ability to be able to set it for amperage is slightly higher end. So when you're looking at maybe an entry-level DSO, maybe you're going to use U-scopes, and U-scopes are great. They're not really an entry level. They do a tremendous amount of stuff, but they don't. They're going to generate that millivolt signal, and you're going to have to convert it over. So why do we want to use a current probe? Well, a current probe gives us resistance problems, power problems, ground problems, and the big key, they're all under normal operating conditions. So the key to this is we're not disconnecting anything. It drives me crazy when I'll be in a shop somewhere and I see a person using an ohm meter, and they're using an ohm meter on something that would make way more sense to use either a voltmeter or a current probe and have the circuit be live. Okay, when you disconnect a circuit, now you're putting an unusual voltage across that circuit with an ohm meter. Ohm meters have 9-volt batteries in them. The most you can get out of it is 9 volts. Okay, so now when you go and you look at a car, well, let's see, this circuit's running on 5 volts. Well, that means your current probe, not current probe, your ohm meter might be putting too much voltage to it. So keep it in mind. Okay, current probe connections are real easy. Now, of course, I chose an obvious car, and let's do the simplest one we can. So, here's an old 3300, and I'm just out of fuel injector wire, real easy, because we have to recognize, what we're dealing with here most of the time are series circuits, which means we can connect anywhere in the circuit. Make sure it closes completely around the conductor. If it doesn't close completely around the conductor, you're not going to get anything accurate and any kind of accuracy. Make sure the battery is fresh. Okay. If you don't have a spare battery, you don't have a battery. Okay. You ought to at least have one additional battery because you never know. And the ability to take it out and the ability to be able to do it relatively fast. See, in my, this, by the way, I'm in my den. Okay. And that's one of the other, I just dropped the screwdriver. Well, hell with it. One of the advantages to like this EM330, and I know most of you don't know my wife Carol, is Carol let me bring it into the den. She said it better not leak on the floor, which it won't. But anyway, so we have to make sure that with a battery, we check the battery and we zero adjust. As the battery runs down, you have to zero adjust frequently. Now, one of the things that I'm a believer in is using the DSO very, very early. Use it in a basic class. I used to have a basic electricity 150, and we started them out with light bulbs and resistors and wires and a power supply. And about 2 weeks into the class, and it was a 10-week class, about 2 weeks into the class, I brought the DSOs out. And we were lucky enough to have enough DSOs, all different varieties, but enough DSOs so that we could use them and introduce them. I like to use it and try to get the students to see what's actually happening. And that's the key. And I'll show you how I do it in a couple of slides here. So I'm going to initially draw a simplified electrical diagram. I'm going to add a DSO to it. And once I've added the DSO to it, then I'm going to have the ability. God, okay, let me flip here. Okay. Rick, you seeing the whiteboard?
Yes.
Okay. Gee, it was silence there for a minute. It was scaring me. Okay. You all have whiteboards in your classroom. Go up to the whiteboard. Now define it. So talk to a student and say, or a group of students, and say, what's B plus? What does that mean? And obviously they have to get across that B plus is battery voltage. Okay. Now we're going to come across and we're going to go to a fuel injector coil of wire. Okay. Now you have to explain some things about magnetic field, and hopefully you've done that already. But the point that I'm trying to make here is, and you notice I'm using red on purpose. Don't use black just yet. Okay. So I've used red to try to indicate that if this circuit is open, like I've drawn it, then positive is everywhere on this, and it won't switch to anything until we close the circuit to ground. Okay? Change colors again and say, okay, if I stick a voltmeter, and I'm just going to draw a voltmeter like this, analog voltmeter, right there, then what does actually the voltage, or what is the voltage at this point? And, we say, okay, so the voltage at this point is going to be, 12.6, let's say, or whatever. So in other words, if I want to define this, so I'm going to put 12.6 over here. Okay. You can use anything you want, but be realistic, because I'm using the term B plus, and B plus is battery voltage. So if the car is not running or the the charging system is dead, we're on a battery voltage is 12.6. Probably more like 13 and a half to 14 and a half. But what's the point? Why am I doing this? I'm doing this because when we close this circuit, ground flows all the way back to the resistance. So we've got a resistance here, and that resistance is generating a magnetic field. And that magnetic field is what's going to open our fuel injector. And after it opens the fuel injector, then we're going to be able to, then we're going to have the student recognize that this voltage is going to go from positive 12.6 and eventually will go down to negative. Okay, so if we do this, we have the ability with the student to have him see, and I keep emphasizing to the students, you have to see the voltage, you have to see the current. So what do we have here? We have a voltmeter, which obviously is going to be a digital storage oscilloscope, and this voltmeter is going to show us whether there's an open circuit or a closed circuit. That makes sense? Okay. Okay, if we add the cursors, we can identify voltage and time and everything else. But the whole purpose is to have the students draw and identify voltage. So I have the student draw the circuit just on a piece of paper, and then I have them put a bunch of lines on the side. And what I asked them, I said, okay, using the DSO and using the cursors, what is battery positive? Okay, so here's a Toyota as an example. This is off of a 2007 Toyota. And if you're familiar with Pico, you realize that I'm kind of cheating here. I've got a voltage waveform, and actually I have a current waveform here also. I just have changed my screen around. Okay, so now a student looks at this, and you ask the student, what is B plus? Now, we can measure B plus right here, okay? But to do that, I'm gonna have to go live, and I'm gonna do that in a second here. But that's the voltage. And then what happened right here? We turned on our fuel injector, and we applied, in theory, 0 volts or very, very close to 0 volts. After the fuel injector is no longer commanded on, this is the command, and Dick talked about command versus actual. But once that command is, we get an inductive kick right here. Okay, now here's your first change. Assuming you teach it this way, then not the next thing, but somewhere along the line, you have to take a good look at GDI, gas direct injection, because you're not going to see that inductive kick. And I'm going to get to GDI, so I'll hopefully answer questions at that particular point. But what we can do, and I'll tell you what, let's get out of this, and let's load. I don't want to load that. I want to load this. Let me load the Pico. Takes a little bit of time. Now that, by the way, that's a lot of noise because the system right now, I'm not going to use. I'm going to go back and I'm going to pick up. Okay, so I'm going to open up now. One of the things is when you start, if you start teaching this, you need to have some kind of a filing system. Okay, so I'm going to go. It says Alex. That's my granddaughter, by the way. I stole her car one day. That's that Toyota. Okay, now this is the one. This is the one that we've got. That I've been showing you just the top half of this. Okay, but here's what I want the students to do. I say, what is that voltage? So now what they should do is take a cursor and bring that cursor down and put the cursor right there. 14.11 volts. Now, this is, I realize, a little hard to see based on your screen size. Okay, but I've got 14.11 volts there. Again, at this point, we spend time with the student and we say, what does that represent? Well, you're putting 14 point, call it 14. You're putting 14 volts through the injector. That's a real common misconception. What you need to teach them is you're putting 14 volts across the injector. This is the applied excuse me. This is the applied voltage. Okay, so once we get the student to that point where they recognize that and say, why is it showing there? Why do you have, why do you have 14 volts? Well, you have 14 volts because there's no current flow. Now this, by the way, I apologize for this pattern. I was experiencing a difficulty with my current probe and didn't realize it. And but anyway, at this point here, from this point to back this way, there's no current flow. That's why the voltage is up. So you start relating the two things. Now, what happens when we want the fuel injector on? The PCM says, okay, I'm going to apply ground. Actually, I went a little too far. This is a little hard to do, but anyway, basically zero. I got 829 millivolts, and it's negative, but base for all practical purposes, it's zero. Well, now wait, what's happening here? Why did this go to zero? Well, it went to zero because inside the PCM, we have applied a ground. Once that ground is over, that may be a bad way to say it, we generate an inductive kick. And the inductive kick in this particular case is 114.5 volts. So that's pretty high. And again, this is a good spot for you, not for the student yet, but for you to recognize this inductive kick on GDI, most GDI vehicles is shunted to a capacitor. And that capacitor, or series of capacitors, stores that voltage until the next firing. Okay, until the next firing. So I just kind of keep that in the back, and we'll talk about it a little later. Okay, next question for the students. How long was the fuel injector open for? Well, we have them use the time cursors like so. How long was it open? 2.338 milliseconds. Okay, and that's an average amount. Now, is that the same kind of an amount you're going to find in a GDI? Ooh, no. That's like 4 times greater than most GDI. Most GDIs are running less than a millisecond. My one example I have here comes off of a Hyundai. It's either a Hyundai or a GM, one of the two. I don't remember what I've put in here, but I mean it's running at half a millisecond, 0.5. Well, how can it run at 0.5 milliseconds? It runs at 0.5 because of the high pressure. This car is running way lower pressure. Okay, so what we've done with the student is we've said, what's the applied voltage? What's the ground voltage? How long was the fuel injector open for? And what was the inductive kick? And I just said something wrong. What's the applied voltage? What's the ground voltage? What is the command time for the fuel injector to be open for? And Dick spent some time and talked about this, but let's do this live. Let's see how good my granddaughter's car is. It's running 2.3 milliseconds. Now, what I usually do is I write that down. So I'm going to put down 2.3, and just call it 2.3 milliseconds. Now I'm going to change my time cursors, and I'm going to put it at pintle bump to pintle bump. $1.5. Okay. What did Dick say? Dick said we're supposed to be within a tenth of a millisecond, and we're at 0.8. So we're at 0.8 of a millisecond, meaning for the fuel injector to be open for 1.5 milliseconds, which is what the vehicle needs, the PCM had to command it to be open 2.3 milliseconds. That makes sense? Okay, you can do this on any fuel injector, and that's a big key, because what it does is it gives us the ability to be able to determine and show a student, here's why you have to keep the fuel injectors clean. If you have the ability to clean fuel injectors, which I hope you do, take this car, clean the fuel injectors, then do this test again. Now, you might not get all the way down to 0.1, but you will find a significant difference. So in other words, this car, 1.5 to 2 is 5.5, 0.8 milliseconds. 0.8 milliseconds. This 0.8 milliseconds is significant enough that if you clean this, I would guess you'll cut this in half at least. Okay, and that's just a guesstimation. But this taking the cursors, and you'll notice I did not put 4 cursors on. I put 3. If you put 3 cursors on, your DSO is using its ground voltage, excuse me, its ground voltage off of the connection that you have made at the battery or wherever. Okay. All right. So let me go back, see if I can get. Okay. Again, what does a current ramp indicate? It indicates resistance. Indicates when injector opens. There's a pintle bump there. You know, middle 1/3. Voltage indicates when injector closes. This is all kind of a review, and this is the same Dick Krieger slide where we check for dirty injectors, and we've just done that. Here's another example, and this is another DSO. You know, I had guys say, "Oh, I got an old DSO. It probably won't show that." No, this DSO is out of the early 90s. Okay, this is a fluke, and you know, the bump is still centered. The bump is real easy to see. Okay, and this is a current waveform, so you can connect a current probe to just about anything, and that's an important key here. Okay, all right, I'm going to skip through this because again, I've just done this with what I would consider to be a live vehicle. Now let's jump right into direct injection, because that's, you know, one of the important things is change, and change is, you got to be teaching. You know, direct injection's been around. I mean, it's not brand new. I mean, the likelihood of finding direct injection on vehicles is really very, very, very strong. So when with direct injection, we use high pressure fuel, and most of the time the high pressure fuel is delivered to the fuel injector through 2 fuel pumps. So we have a low pressure pump, which feeds a high pressure pump, and a high pressure pump, which directly injects into the cylinder. Okay. Pressures in the thousands is not uncommon. Now, that Toyota was probably running, I don't know, 30, 40 PSI, something like that. It is not uncommon to have pressure in the thousands. Okay. And the other thing about it is, fuel injectors are typically pulsed. Now, I asked a whole bunch of people that I thought really knew a lot of stuff about why they pulse injectors, and I got Zippo answers. Finally, I took an ex-student of mine who was a GM service manager or service writer, and I said, "Can you ask that question? Because you have." Well, anyway, he asked the question about, you know, 4 or 5 weeks later. He got back the answer that what they want is they want to have a bunch of mini fires. So if we pulse the injector rapidly, we start the fuel burning in a series of mini fires. The mini fires causes to ignite the entire charge. Remember, especially with direct injection, we have a lot of action in the cylinder. Typically, we squirt the fuel at a dome or at a concave surface on top of the dome of a piston, so that what happens is the fuel hits it and spreads out. So now we cause this mini fire. Okay. Now, first thing, if you haven't done this, you need to, but you got to recognize a couple of things about this. Do you see an inductive kick? Well, I'll tell you what, let's go through this. Okay. Here's the first time the fuel injector stays on. Okay, it's a voltage waveform. Okay. Second time. Okay, so we pulsed it. On this one, we pulsed it twice. And what happened is, you'll notice there's no inductive kick here. There would normally be an inductive kick over here. Where'd the inductive kick go? Well, the inductive kick went over so that we could supply, I don't know if you can see this, but we're running about 60 volts, 60, 62 volts here. So, you know, your student wants to know, well, wait a minute, you know, Mr. Krieger, I thought you said the car ran on 14 volts. Where'd they get the 60 volts, 62 volts? It got it from the inductive kick from the previous cylinder. Now, think about this. I got a bad coil or a bad fuel injector. Okay, it's not putting as much injection as possible, and that cylinder may partially misfire. What about the next cylinder? If you don't have a good enough inductive kick, the next cylinder might not work at all. So it's not uncommon on GDI to have two cylinders in the firing order next to one another that are both misfiring. So think about that. You got two cylinders, and it's really being caused from only the first fuel injector, not necessarily the second. So when you come up with not a random, but a P0301, okay? So now what does that indicate? It indicates that cylinder number one is misfiring. And then you look at ignition looks fine. You look at fuel and you say, nah, fuel's not right, okay? That's all by itself. But if you wind up with a P0301 and a P0304 on a four-cylinder that's 1, 4, 3, 2 firing order, then 4 might be being impacted by 1. So what's the deal here? Well, a couple of things. The first thing is, if you replace a fuel injector on a GDI car, you are replacing the fuel rail, because they can. There's thousands of psi here. This, by the way, this is off of our Hyundai bench, a Hyundai bench that we have. That I forget what the part number is, but it doesn't really matter. But it's a Hyundai and it's GDI. We have other benches, by the way, in our stockpile, including our cruise bench, which is also has start-stop technology, and it is also GDI. So you can do all these things on engine benches, or you can do them on the vehicle. They're a little harder to do on the vehicle, though, which is where the engine bench makes some sense. But keep in mind, so I've got this P0301, P0304. Is it possible that number one is only affected? Or is the problem? Answer, yes. But think about it. If we take this thing apart and put one fuel injector in with a new fuel rail, bolt it in, fire it up again, come up with a P0304 that's still there, we're talking about another fuel rail and another fuel injection. Fuel injector. If you talk to the smart technicians that are in the field, if they're going to put on a fuel rail, you got a 4-banger, they're going to put 4 fuel injectors in. Even though they only have one that really shows bad, they're going to put all 4 in, because they don't want to have to go through this again, especially at the cost of things. Now, let's talk a little bit about how it does this. Number 3 in here is a fuel pressure sensor. So we have a sensor which generates a voltage, and the voltage is interpreted by the PCM as low pressure. From the low pressure, and here's low pressure, and this is on, I don't know what's on. It's on a GDI car. It's probably on a GM, I would guess. But anyway, the low pressure is running at 46.98 psi. And remember, what's the purpose of that? Well, the purpose of that 47 psi is to feed the high pressure pump. So is it important to look at low pressure? Yes. If you have an issue, start realizing that you need to look at low pressure, high pressure. You need to look at everything at the same time. You'll notice that there's a calculated load here, and I've reprinted it down here. You've got about a third load, okay, which is good. If you go up to this and you see 47 psi at 90% load, that pump is on its way out. Okay, you'll typically find them between 20 and 40% load. Now, some of your scanner, this is where I'm going to put a plug in for spending some money in your shop and have at least one good scanner, one bi-directional scanner. And by bi-directional, I mean that scanner can do more. It'll be able to do more. Obviously, you can get this off of manufacturers' ones, but you can get it off of other things. This happens to be Auto Ingenuity, and Auto Ingenuity does a pretty nice job. Okay, so we got 47 psi which is going to feed, and it's going to be how does low pressure sensing? It's done with a pressure sensor. If there's no pressure sensor, like some cars do, then the PCM is programmed to look at the pulse width modulation of the pump. So now let's back up. Okay, if I'm the PCM and I'm looking at pulse width modulation here, it's running about a third. So I have about 30% or 33%, and I have 66% off. So the pump is pulsing on, off. Now, what happens if this pump is somehow unable to supply enough fuel? Is that percentage gets higher and higher and higher. So whether you have a pressure sensor or you're looking at pulse width modulation of the pump, you're going to see that number get greater. See over here, the second one down, and that's 80%. You're at the point where that's no good, way no good. Okay, 50%. You better start thinking about doing a fuel pump on it. But this one makes more sense. You're running about 20% pulse width modulation. Hey, high pressure pump. Well, how does this high pressure pump develop pressure? Well, they have to be driven by something. They're driven by camshaft most frequently, but we do have vehicles on the road today where they have an electric motor running the high pressure pump. It's a hell of a motor, but it's running the high pressure pump. Okay, so the roller following bucket types, and it really doesn't matter. You're not going to redesign the car, but you may get the question from a student, well, how does this thing be able to generate that much power or that much pressure? And the answer is it's driven by the camshaft most commonly, and it's got some kind of a roller or a follower. Okay, these babies can put up pressures between 500 and 3,000 psi. And this is why you are replacing the fuel rail. Do not let any student disconnect a fuel injector off of a fuel rail on a GDI, put a new fuel injector in, and reinstall the fuel rail. You're making a big mistake from your liability. Okay, keep that in mind. You got a pump running, 2,000 psi, and all of a sudden you have a leak. And where is that leak? Well, it's under manifolds and everything else. Okay, so in other words, now once the fire starts, you've got a pool of fuel in there, and this car is toast. And hopefully the owner of the car is smart enough to unfasten the seatbelt, open the door, and run. Okay, these high pressure systems, when they go up in smoke really. I mean, you'd have to literally be inside the fire department and have the firemen be standing there and have the ability. Pardon?
For the $15.
Oh, really?
Yep. You know what I'm saying? The people who visit stuff.
Can we turn off our microphone? Okay, so this electrical pressure regulator, and that's the solenoid you see right on the top of that. That electrical pressure regulator controls the pressure coming out. Okay, there's a pressure relief valve in it, and it's normal to hear some noise. Okay, if you don't hear noise out of it, especially this kind of a characteristic clicking, you can guess that someone has put the wrong oil in the engine. You cannot run regular oil in these engines. They have to be synthetic. So, and good synthetic too. So you have to be running that, otherwise you tear up the cam. And once you tear up the cam, you don't hear the pump anymore. Okay, if you unplug this, and I recommend that you don't have students do this. If you want to do it, that's fine. You will find that the system will default to either low or high. It depends who made the car. Okay, so you unplug the connector and that pressure goes sky high. If you have any leaks, you're going to have greater leaks. Keep that in mind. Here's a little cutaway of the pump, and it's hard to see, but anyway, now let's switch over and look at high pressure. Okay, again, I'm using auto ingenuity. You're going to use a scan tool on this, and again, it better be a halfway decent scan tool. So what does this thing say? Here's a car sitting at idle, running 632 psi. Now remember, we fed this with 47 psi. So we had the pump generating 47 psi, pushes that 47 psi pressurized fuel to the high pressure pump. The high pressure pump boosts it up again. Now we're at 632 psi at idle. Okay, and that's what the pulse width modulation looks like. Now the pulse width modulation is really there isn't a lot here. Okay, it's probably around 50% or so, meaning this pump is kind of loafing along, but we're sitting at idle. Okay, good scanning imperative. I can't stress that enough. And what it'll give you is the ability to be able to look at things at the same time. Fuel pressure 565. Now let's take it and let's do a pressure, or let's increase the pressure. So I'm going to, again, this is something I do not recommend you have students break torque. Okay, I think it's just you're asking for trouble, and that's part of it. So when you break torque it, you should do this so you understand. In this particular case, we go up to 1673 psi. Think about that. 1673 psi, and that's only half load. Now let's take a guy who throws a boat on the back of a 3,000 or 4,000 or 5,000 pound boat, or a travel trailer, or just a fully loaded pickup truck that's got the bed of the truck loaded with concrete, whatever. This pressure is going to be way higher than that. So I think it's important that when you talk to students, that you get across to them the idea that it is the pulse width modulation of the pump that controls the pressure. And remember, when we go back, let's see, which side do I want? Okay, when we go back here, we only have a total on time, and on time is measured from here to here. That's it, from there to there. Okay, we only have a total on time of half a millisecond. Well, wait a minute, how's this car roll down the road? Well, it rolls down the road because you've got 1673 psi. So you don't need to have the fuel injector open for very long. Now this does a couple of things. The first thing is the fuel injector runs a little bit cooler because it's not open that much. When you put magnetic field and you keep that magnetic field on for 3-4 milliseconds, the fuel injector tends to run a little bit hotter. So we're finding on the road, GDI fuel injectors work for a longer period of time, but when they go big time. Okay. Now let's look at the pressure regulator. Now this is off of our bench, our Hyundai bench, but you can do it on a car too. You just have to back probe the connector. Okay. So we're pulse width modulating. You can see this right here, and we're sitting at idle. Now this might not make a lot of sense, but let's compare it to 2,500 RPM half throttle, half load. No, actually, I'm sorry. This is 2,500 RPM with no load. It would be even worse. Look at the difference here. Okay, idle, 2,500 RPM. So we've got a tremendous amount of fuel capability. Now notice there's small little pulses in both cases. Here the pulses are on for a little longer period of time, but here you just have these massive number of pulses. So this is how we get the pressure. And this pressure was at that point on this car was running, well, it was running somewhere between 600 and 1600. So I'm going to say it's probably running around, 700-800 psi, because we don't need a lot of pressure until we put a load on it. Okay, now I want to show you just a couple of things before we take a little break and we go into ignition. We used to do IM 240 certification, and we had a failed car for CO. Now, obviously, we don't have a lot of IM 240s being done now anywhere, But if a car comes in the door with a P0301 or 302 or 304 or whatever, you've got a misfire. You can see that misfire on an oxygen sensor. But when we look at a good fuel injector, this is a current waveform, on the same car, here was the bad one. So relating the current probe as a diagnostic tool, if you have if you have a P0301 and you got a 4-cylinder car, that means you got 3 cylinders that are not misfiring. So we use one of them as a reference. And that's what I did in this particular case. Again, an older DSO. Okay. Not many of these around anymore, peak and holds, but that's what a peak and hold looks like on a GM peak and hold on a current probe. And you'll notice that you have, that you've got, you got 4 amps to open it and 1 amp to hold. So here's your 4 amp pulse. There's your 1 amp there. And then remember, this is a current waveform, so there's no inductive kick or anything that's showing on there. Okay. My last one. Look at the current ramp, not the voltage. Look at the current ramp. Okay. This turned out to be a PCM ground problem. So that, that runs the thing. Now, Dick did a really good job of this, and I'm not going to. Okay, it's not that I'm not going to do a good job, but I just want to show you an example. Okay, he went through calculating pump speed. There's a good pump. So the good pump on the right-hand side there, we find a repeating pattern. How many humps? We got about 8, and that's pretty common. 8 commutator bars. What's the time between the repeat? The time between the repeat is 9 milliseconds. Now, maybe you didn't catch this from Dick, but I don't call this 9 milliseconds. I call it 0.009 because all of your math does not work if you put 9 milliseconds in. You have to write it out. So in other words, it's 0.009. If we divide 0.009, excuse me, into 1, we got 111, which means this pump spins in 1 second 111 times. In 60 seconds, it's running 6,660 RPM. The general accepted bare minimum drop dead may not run RPM is lower than 4,500. Okay. And these are kind of obvious, but I want to get to the next one. Okay. Same car. This is how the car came in. By the way, it came in at the end of a tow hook. But anyway, so here's the same car. We have reduced pressure, we have reduced volume, and I tell the students, go over and calculate the fuel pump speed. Real good activity. They check it, come back and say it's 1,700 RPM. Now that's a bad pump, and then we replace it, and there's the same vehicle with a good pump. Notice 2 things. First of all, you have way more pulses in the same time period. And second of all, it cleans it up tremendously. If you look at your scale, this scale right here was 2 milliseconds per division. Whereas this one, to get a decent pattern, I had to put it to 5 milliseconds. Well, right away, that tells you the pump is not spinning near as fast. And again, in this particular case, it was spinning, at a very, very, very reduced RPM. I don't remember whether it had a high or low current. And the other thing is, some scopes will allow you to AC couple. Now, what AC coupling means is that we look at it's a DC pump. But what happens is because you have spinning conductors and magnetic fields, you generate an AC voltage. So you have an AC voltage riding on a DC. On some scopes, the AC voltage is easier to see than DC, but you should be able to do it in either case. Okay. So there's a big question. What ignition systems are in use today? Now, I got to be perfectly honest with you. There is a relatively new system that is on the market that's being used by a few manufacturers that is not in the slide series. Okay, come back next year and it will be. But anyway, please, guys, no breaker points. You know, I had a guy in a class that I was teaching. I won't even say what state, but not Florida. I'll tell you that much. And he came up to me and he said, "I don't have time to." I was teaching CAN bus. I don't have time. Well, I understand. Time is a real problem, you know, in schools. That's for sure. And so we spent a little bit of time, and I asked him. I says, "Okay, so look at your curriculum in terms of what you could get rid of. Are you teaching carburetors? Well, a little bit. Okay. Are you teaching breaker points? Oh yeah. Aren't you having trouble finding breaker point cars? Oh, I've got a bunch of them on stands. Oh, come on. You know, well, we're talking about technology that's over, you know, we're talking about literally 45, 50 years. Don't do that. Okay. There are limited systems, excuse me, still on the road with distributors. Not a lot. Not a lot. Without a distributor, and this is the most frequent one, three we find. Now, of these three, COP, CNP, and waste spark is going away at buggy whips. I mean, we're not finding many vehicles now being produced. There are some now being produced that are still using waste spark. Probably the most common thing is coil on plug. Okay, coil on plug, and it's been around for a long time. I mean, coil on plug probably I'm going to guess and say came in the early 2000s. Okay, so it's been around for quite a while. There are a few, but not many major differences in GDI. They're very, very, and I'm sorry, I wrote major there. I meant minor. There's very minor differences in GDI. Okay, so what do all systems have in common? Obviously, it closes the circuit to the primary, current flows through the coil, and that we call dwell. And I know those of you a little bit older remember what dwell was the amount of time breaker points. Yeah, okay, well, dwell is the amount of time current flows. That's what the definition of dwell is. Okay, what does dwell do? It saturates the coil, both saturates the coil primary, meaning we have a magnetic field. Okay, then something opens the circuit to the coil, module, coil itself, whatever, but something opens it. That causes the magnetic field to collapse. And once the magnetic field collapses, we induce into the primary and secondary voltage. We have a spark, and then we dissipate the remaining energy. So that's basically the idea behind it. And what you can do is, especially if you've had these students before, is you can go back and you can say, okay, now what do we have to do to make this into another into an ignition? Well, we have to connect another coil of wire. So there's my other coil of wire. There's my spark plug. Okay, and this connection here may be either B plus or ground. It really doesn't matter. And so I'm going to tap it up there because it's good on a diagram. Now, this is a terrible diagram, and I know you're better artists than I am, but you know, if you keep the wiring diagram for a fuel injector, and then you say, okay, now can we make this? Does this work for anything else? Well, yeah, it works for relays, it works for control modules, it works for a lot of things, and then we add an additional winding, and that additional winding is what gives us our spark. Okay. All right. Now let's go back. All right. So what does this look like on a DSO? Well, again, get your students to measure, okay, with a cursor and ask the students the same questions. What is the level of B plus, and why does it have B plus? And the answer you're looking for, and this is a hard answer for students, but it goes back to voltage drops. Why is there B plus at the start of the pattern? There's a B plus at the start of the pattern because there's no current flow. Okay, there's no current flow. Why does the pattern go down to 0? Well, it goes down, or some lower level. Doesn't this, a lot of cars never hit zero, but anyway, why is it lower? It's lower because now all of a sudden we have current flowing. When current flows through resistance, you create a voltage drop. When current flows through resistance, you create a voltage drop. You know, one of the things that I did in my classroom is I would take things like that and I would have it laminated and I'd stick it on a bulletin board somewhere big enough so I could walk over to it and point to it when the student asked a question. Okay. And it was in the classroom all the time. I had things like what is B plus, what does ground mean? You know, you put it in front of them so the student. Anyway, so then it creates a voltage drop and we wind up with a spark. So there's our full pattern. And we can actually go, and maybe we should. Let's do. Okay, you should be seeing Pico on the screen, and I'm going to open up a ignition. Okay, here's a primary ignition pattern. Primary ignition. And there's a couple of things that this shows us. But one of the things that we have to do is we have to look and ask ourselves, okay, what's really happening here? What's happening when we turn on primary current and primary current builds, okay? And again, you can have the students with cursors say, oops, wrong cursor, I want my time. Okay, how long was primary current on? Okay, primary current was on for 2.981 milliseconds. And that's going to become important. There's another spot in here where I talk about what it really means. But you know, it's the ability again to be able to look at the pattern and have a student interpret it. We start with a higher voltage. We drop it down. This is the beginning, and actually these patterns, I'm not sure why they're not synced, but anyway, this is the beginning. And then this is where current is flowing at zero. Now at 0 volts or at some low voltage. And then what's going to happen is we're going to wind up with something called current limit. And for this, I'm going to go back to the PowerPoint. Okay. And again, let's talk about primary current here. Primary current rises to one of two things. It either rises to a level based on time, and then we turn it off and fire the plug. Or it rises to a specific level and hangs there, and that's called current limit. Now this pattern right here, and I don't even know what this is from. Let's see. Anyway, I don't know. Oh, it's off of one of our ignition trainers. Okay. Right here, 0 amps, current goes up, and then it doesn't fall back down again. Instead, it stays at that level. This is a vehicle that has current limit. Okay, so what's the point? You teach the basics of ignition by using voltage and current, and use a DSO. Teach them the basics. They're going to use these basics every day, and you might as well use them. You have to get across the idea of voltage drop, current ramping, and the sequence of events. Now, this is a real nice pattern, and you can pick up real good patterns, you know, off of a whole variety of cars. What I usually like to do is I like to try to collect patterns from a variety of different vehicles so that you have some choices. Okay. And that's where you're going to use the dual trace function. Now, I am not saying this to be anti the U-scope. Just the opposite. I have a U-scope. I use it. They're wonderful. They're great teaching tools, but they don't have dual trace. And there are things that you're going to want to use dual trace for. One of them is fuel injectors. Second one, ignition. Third one, CAN bus. Now there's other ones, but those are the ones that you absolutely will find and very beneficial, ignition and fuel. And the third one I said was CAN bus. That's where it's a necessity. You have to have a dual trace oscilloscope to be able to do CAN bus diagnostics. Okay, so what does all this primary stuff do? Now, this is where it gets kind of tough on, not so much on the DSO, but tough on the vehicle. If you don't have a spark plug wire, you're not going to get a pattern like this, okay? The primary is going to generate a voltage spike in both windings, and have the students look at primary first. And the reason I think you should look at primary first, primary means first. Look at it first. Okay, don't have them get into some oddball, or some unusual kind of a pattern, and that doesn't make a lot of sense. Okay, so have the students look at the primary first. Have them read the voltage. What happened here? What happened here? What happened here? What happened here? Okay, and when you get to a certain point, you have to start talking about this induced voltage. That's higher than B plus. What do we mean by that? Well, if you take a look, this pattern right here, this is a what am I doing? 50 volts, 50, 100. Yeah. This is a primary running at about 275 volts. Now, is 275 volts enough to fire the spark plug? No, of course not. And that's where the secondary comes into play. Now you'll notice I just switched type of ignition coils around. Okay, I'm now on a waste spark. I don't care. It really doesn't matter. The important thing, and you can block out half of this diagram if you want, is to get the students to understand that the secondary is very close to the primary. And what happens when the induced primary field collapses, it cuts across both the primary and the secondary, and it generates a spark. Okay, so the plug, and this is important, the plug is connected to the secondary. Now notice on this one, and I apologize, it's pretty small. What have we attached the other winding of the secondary to? We've attached it to ground. It really doesn't matter. When you're generating 6, 7, 8,000 volts, you can push current anywhere you want. Okay, basically the car's running down the road at 14 volts, and you have a spark plug that wants to run at, let's call 6,000 volts. Well, 6,000 volts, you can connect the secondary of the coil to the primary. You can connect it to negative. It doesn't really matter. Okay. So we're going to generate a high enough voltage to jump the gap, and that obviously is what we're going to do. Okay. And here's the important thing: burn time. Now, this is not new, but it's something that I'm kind of a bug on, and I don't think it's taught enough. If you're an old Sunscope person, you remember that in the Sunscope classes, the 32-hour course, which Sun Electric taught for, 100 years. Okay, from the 60s, they taught that class. They never said a word about burn time. It was voltage. You should have a firing voltage between 6 and 12,000 volts. Okay, and then we just beat that. I taught for Sun. We just beat that into the technician's head. Well, partway through, realized that the voltage wasn't near as important as how long the spark lasts. When we started leaning out the mixtures, having less fuel in the cylinders, less fuel, getting down to almost nothing, that's when burn time became really important. We need that spark to last long enough time that it will allow the mixture to float past the electrodes and get ignited. And that's the key. We've got to get this thing ignited. Remember when we were talking GDI, we pulsed the fuel injector for the same reason. So now you pulse the fuel injector and you got a burn time of 0.8 to 2.0, you're in business. Okay? It's got to be greater than 0.8. Now, where can you measure this? Well, here's the primary again. Okay? So if we look at this, now you're running a half a millisecond per division. So I hope you can see my arrow. There's a half a millisecond. There's 1 millisecond. There's another half of a half or a quarter. So this burn time is 1 1/4 milliseconds. Well, it's supposed to be greater than 0.8, good or bad? Good. Okay. And the key here is to get the students to recognize that burn time is the most important because it allows the mixture to burn. We got to get it ignited. And that's important here. The mixture swirls past the plug. Okay. Misfire. Misfire. Get the misfire burning without or get the mixture burning without misfire. I started to say get the misfire burning without mixture. No, doesn't work. So mixture, burning, no misfire. Now, how do we measure secondary voltage? Well, that's a challenge. It really is. Old scoops did it by connecting into or around the plug wire. You got a plug wire? Actually, the real old scopes did it by connecting to the coil wire. You got a coil wire. So if you don't have a coil wire, you don't have a spark plug wire, you got to come up with some other method. And that method is a paddle probe. Paddle probes are inexpensive, okay? And they're capacitively connected. Now, it's important to recognize the two ways of connecting something like this would be induction or capacitive coupled. If you inductively couple, you will be able to read the voltage. No scopes don't do that. The paddle probe is capacitively coupled, which means you can't measure voltage with it, but it will tell you whether a spark occurred. And that's important. And it will also give you burn time. Okay. Most of these systems, you can't get to the secondary. So you have to rely on primary, and you have to use a paddle probe to get secondary. It'll show you that the spark occurred. Almost impossible to measure firing voltage, but we don't care anymore. Don't teach 6,000, 8,000, 10,000, whatever voltage you're teaching. No, that's bad. And why is it bad? Take a car, take a modern car. I don't care. It doesn't have to be brand new. Okay. I got a 2016 and 2017 sitting outside. Neither one of those has the ability for me to measure secondary voltage. So is secondary voltage important? Yeah, causes the spark to occur. However, if we can't measure it, we're going to rely on burn time. Okay, the 6 to 12,000, forget that. Okay, here's a paddle probe, and this is on what? It's on one of our trainers again. That's a good thing. I'm using all our trainers. And the burn time, okay, on this particular one, we are running. I think I'm running 160.6. Yeah, we're running 1 millisecond per division. Okay, so at 1 millisecond per division, burn time here is there's my, call it firing line if you want, but it really isn't. Okay, there's my firing line. Here's my burning, and here's where burn ends, and we go into coil capacitance oscillations to get back down to 0 volts. This is burn time right here. So what's the burn time on this vehicle? It's about a millisecond. Well, what's the spec? Easy. Okay. Here's another one. We're running 1 millisecond. This one's running, so there's about a half a millisecond. There's 1.5, about 1 3/4. This is running, less than 2, but it's pretty high, and that's decent. Okay. Actually, when we put the scope on it and we put the cursors on it, it runs 1.86 milliseconds burn time. Wonderful. 0.8 to 2.0 is what you want. You will find if you use this as the spec, you will not replace spark plugs near as often. Okay. And the reason is the spark plugs, the iridium plugs that we have now, go long time. I had a guy tell me, he says, I replace my plugs every 25,000 miles. Really? Why? And it was at that point in time, I had a vehicle that was running 95,000 miles. And I said, those are the original spark plugs in there. And they're doing fine. Okay. Now, let's switch gears here a little bit. Okay. This was burn time. There's an actual spec for it. The next thing is coil saturation. And there's an actual spec for this. This coil saturation is 2.88 milliseconds, and the spec is in red. So the specification is greater than 2.5 milliseconds and we're running 2.88. Now, for students, relate these two together. How do you get 0.8 to 2.0 milliseconds burn time? Well, you get it by saturating the coil and everything. Okay, so how long do we saturate the coil for? If we saturate the coil for a minimum of 2.5 milliseconds, that coil should be capable of generating the spark. Again, you're looking at primary. Okay, this is primary. So what's going to switch the primary on and off? Well, ignition modules, assuming you have one, and they're going to have a couple of choices. They're going to be a 2-function on and off, a 4-function on off, variable dwelling current limit. Almost never see this. Okay, they can be anywhere. You know, the manufacturers can put this damn thing in the glove box if they want, and it, you know, so it, don't look for it. I mean, this is a Ford TFI, and I know it's upside down, by the way, but I wanted the United to show, and when I turned it correctly, it didn't. It was upside down. So anyway, we have to look at this, and we have to ask ourselves, okay, what are we actually looking for? Well, okay, here's the on-off function. It's current. This is current, by the way. Okay, and you will notice that current peaks, and when it gets to that peak, it immediately shuts down. So this is the on time right here, and then it peaks. This is slightly different, but slightly different from some modules. But all modules or PCMs or whatever is firing this thing have to have this function, okay, or it doesn't start. Okay, so we take the coil negative from V plus to ground voltage, current ramps up, that's a current waveform, and how long? Well, again, should be greater than 2.5 milliseconds. But here's what we find reasonably common. The current limit, and this is the same slide that I used before, okay? Why do we use current limit? Current limit prevents overheating of the coil. It allows for enough spark and an increased plug life. Because if you oversaturate a coil, then what you get is a spark that lasts way too long. I mean, you got a spark which lasts 3 milliseconds. You're going to cut the life of that spark plug down. Okay, you should never be over 2.0. So we increase the plug life, and we know it's current limit because it flatlines. If you put the two patterns next to one another, it becomes pretty obvious. The one on the left does not have current limit. It's a 2-function. It turns on, turns off. The one on the right turns on, and turn off is not even shown on the screen. It's off the screen. But we saturate the coil, and once we saturate the coil to a level that'll generate 0.8 to 2.0, then and only then do we add current limit. Current limit is like throwing resistance in. Okay, if you put an ohm meter on some of these coils, they're damn near 0 ohms. They're a couple of tenths of an ohm. Now you think about that, you say, well, okay, if I put a tenth of an ohm across 12 volts, I got 120 amps. Well, that's pretty unrealistic. I mean, you know, the wires aren't that big and everything. So what happens here? Current limit. What happens is we saturate the coil, boom, real fast. How do we do that? By turning on a ground. We turn on the ground, current flow goes wild. And as it starts to rise, it gets to a level, and then the module, PCM, ECM, glove box controller, whatever, throws in essence resistance. So if we want a maximum of I can't read this one. We want a maximum of, let's say, 1 amp. Then what we're going to do is we're going to put in resistance. Well, if you put 12 ohms of resistance and 12 volts, there's your 1 amp. Okay, so we limit the amount of current, and once we've limited the current, that allows us to be able to have control of it. Okay, let's see. I'm rapidly running out of time here, and there's a couple of things that I want to do. So let me. I'm going to skip through some stuff of this. Setting timing. I mean, these are position sensors. They're going to generate a pulsing DC. This is your old style inside of a distributor. but you don't have distributors anymore. So obviously we get it somewhere else. And the place we get it is we get it off of sensors. So we may have, and you can have both. I mean, it's either going to be DC, a Hall effect sensor usually, or AC, a magnetic. Now, these magnetic resonance sensors, most of them, MR sensors, are not, I don't know of any that are used for ignition, but I wouldn't be surprised if that's in the future. Okay. This accentuated blip, that's going to be used for timing purposes. That is not where the plug fires. That is where the PCM sees that the crankshaft is in this particular position. Okay, sometimes both are used, one for speed, one for position. Now, are there variables in this? Yeah, obviously. The waste spark is probably one of the variables. This happens to be what we call a type 2. And there are type 2 and there are type 1s. The type 2 has individual coils. It's a 6-cylinder car with 3 coils. That makes it a type 2. If it's individual coils are bolted, this one's bolted onto the module. By the way, this is a shop car. And if you look down at the bottom of the screen, there are some PD10s, 2 PD10s. This is so that we could capture patterns and not wreck the wires. You can see the students have already broken a connector. So, I mean, you know, important. So with waste spark, we're going to fire 2 plugs, one in compression, one's going to be an exhaust. Maybe the PCM's the module. You know, it varies. This diagram shows it as the PCM is the module, and then that's okay. Okay, or there's a separate module, but again, there's 1 coil for 2 plugs, 2 coils, etc. On down, up to a 12, which has 6 coils. Okay, here's type 1. What makes it type 1? Well, the 2 coils are molded together. Again, these kind of they're still on the road, but they're becoming like hen's teeth. I mean, I don't think there are many waste. I know there is a vehicle that's manufactured with waste spark, but boy, there's not many of them out there. Okay, so few manufacturers allow primary voltage. Okay, use a current probe, primary on-time current ramp. In other words, you have to try to teach the student to look at the vehicle and say, okay, what do I need to know? Well, I need to know burn time. I got to get that somehow. Can I get it off a primary? Yes. Can I get it off a secondary with a paddle probe? Yes. What do you have available? If you have primary available, use primary. If you don't, use a paddle probe. Easy. Okay. Then how long does primary current stay on? Well, you can use a current probe for that, or you could use a voltage waveform if you have a breakout box. Okay. It's tough to get to primary voltage on a lot of these, almost impossible to get to secondary, but we have a B+ feed wire and can use a current probe on it. Here's a good example. Now, keep in mind, this is a question. If I was teaching a class, I would ask for an answer, but this would be a little difficult for an answer. But what kind of vehicle is this? Is this a 2-function? Do we turn on primary current, turn off primary current? The answer is no. This vehicle is using current limit. How do we know that? Because it's flat tops. Okay. Now this is a 6-cylinder car with 3 ignition coils firing 2 plugs at the same time. So when you look here, there, or here, here, you'll notice we have a ramp. This is current, remember. We have a ramp and we have a flat top. But yet over here, this one and this one, there's no ramp. It's straight up. This is a shorted coil. And one of the beauties in the old days, if you had a shorted coil, you took out a module. On a current limit, what happens is your current rises instantaneously and we throw in current limit. So a current limit protects the module. And this is the same vehicle, by the way. So this vehicle started out with 2 bad cylinders because 1 coil was bad. And obviously 2 coils firing here, hit the wrong button, 2 coils firing here, 2 here, and 2 here. Well, these 2 are okay. These 2 are okay because they have current They have some current ramping. It's the 2, which is actually the same coil. Okay, so again, flat top indicates current limit. We turn primary on, we turn primary off, we have current limit. And that's in the wrong order. I should have said we have primary on, we have current limit, then we have primary off. Okay, now here's our most common coil on plug. This is an older Ford. Excuse me, get a little coffee here. Thank you. We have primary voltage is available on this particular vehicle. Primary current is available, but secondary, you have to use a paddle on it. Okay, don't be afraid to teach paddle probes. The other thing about paddle probes is they're inexpensive. That you can put a paddle probe to a student for, I don't know, 30 bucks. And you know, and you obviously don't need a whole bunch of them, but I mean, the nice part about it is this is what you're going to use on a modern car. So send the students out and say, go get a burn time, and for that you're going to use the paddle. Here's coil near plug. Now, what's the difference here? And this, by the way, coil near plug, coil on plug. This style of coil is the most common. What do you got here? Well, you got a PCM, which is controlling a switching transistor. It's not quite as simple as this, but this diagram was drawn for simplicity purposes. So what happens is we take the base of the transistor to ground. We take the base of the transistor, this NPN transistor turns on the ground of the ignition coil primary. So where is the module function? The module function is inside the ignition coils. This does 2 things. One, it eliminates your ability to be able to look at primary voltage. All you can look at is signal, PCM signal. And the second thing is it increases the cost of the coil dramatically. Okay, so keep that in mind. Cost is important here. Okay, so where's the module? The module is inside the ignition coil. What controls timing? PCM. When you turn off primary current, you fire a plug. So the PCM is in charge, and the PCM is all the inputs of temperature and speed and load and mass airflow. It's got all these inputs that it needs to be able to sit down and calculate. I want timing set to 18 degrees before top dead center. Boom. So it fires it. Okay. PCM control actually allows for each one of these 4 coils, and this is on a V8, by the way, because I just noticed a coil 2468. This is one bank. Okay, that it allows the individual coils to actually have individual timing. It doesn't really happen that often, but it can. Okay, short, tiny little plug wire. Okay, and here's what they look like. Now you can't see the plug wire, but I shot this one. This is on a 2000 TA, 2000 Trans Am. Okay, with a V8, 4 ignition coils. And these ignition coils, they're concerned about keeping that switching transistor and the circuitry cool. So they put a heat sink on it. Okay, so what can we measure? What can we see here? We can see primary voltage. We can see primary current. Primary current's really important here. We can do secondary voltage because we have a plug wire. This is an ideal thing. Listen, I hope you got something out of this. I really do. I'm gonna actually let me leave this for a second here. What are we looking at? Well, this happens to be from a 4-cylinder Malibu, but the important thing about this is a coil on plug where the ignition module is inside of the ignition coil. Okay, so we start at basically 0 volts, And then this is a signal from the PCM. This is the only thing you can really measure. You can measure primary current, but you can't really measure anything else. So this is the signal that go, and let me edit that last thing. You can use a paddle probe, but this is the signal that comes through from the PCM. Okay. Now, if we take our time cursors and we set up our time cursors, what was the spec? Remember that number? I'm not a believer in you memorizing things. So again, what I did in my own classroom is I put a poster on the wall, and the poster said, burn time 0.8 to 2.0, primary on time greater than 2.5 milliseconds. So it was in front of the students all the time. This primary on time, this is what you're really looking at here, is 2.88 milliseconds. So the 2.88 milliseconds is being used. It's coming from the PCM, and with it coming from the PCM, you got a real good chance of being able to see it and do everything else with it. I want to do one other thing with you, okay? And for that, and I'm going to open that again. I didn't really want to close that, but anyway. So we're going to open Pico. Now I don't know if you can hear it, but I've started the EM330, and I'm going to go to the ignition driver. And again, this is one of the advantages. X222 pin is okay. Now, the reason I'm showing you this is for a couple of reasons. The first thing is I want to give this a nice fill the screen. You'll notice there's a lot of noise there, but the first thing I want to do is trigger it. So I'm going to go down to the trigger, and I normally trigger off auto. And then once I have the trigger, I move it somewhere. Okay, that's good enough. That's good enough right there. Now, this is a terrible pattern. Why is it a terrible pattern? Well, any vehicle that has the hood up allows the generated radio frequency, RFI, to get into the scope. I don't care how good your scope is. Okay, so what you have to recognize is we have to use some filtration. Now, there are filtration or attenuators that are used that are external on some. Pico builds it in. You don't hear low pass filtering? You see what happened as soon as I turned on low pass filtering? Here, let's turn it off. Okay, so what low pass filtering does is it filters out the high frequency crap that's running on the signal. Okay, so with this, and by the way, this is controllable, and you can see, you see the angle change? In other words, I've got to get the right amount of filtration in. And my goal is, no, I shouldn't say goal, that's the wrong thing, is I find typically 10 kilohertz gives you a pretty decent pattern. Let's make it even bigger than that. Okay, now let's stop this. And this, by the way, this is a live pattern. I don't know if you can hear it or not. But anyway, it's a live pattern. Okay, so what does this pattern tell us? Or what can we use it for? We can use it to determine how long primary current was on. This is the pattern that's coming off of the PCM control of coil number 1. Coil number 1. So I got 4 coils on this thing. Okay. So now I've frozen it so that I can play with it. How long is primary current supposed to stay on for? I hear the crowd yelling. Greater than 2.5 milliseconds now. Primary current is on for 3.8 milliseconds. Pretty high, but that's, this, when you're dealing with like the 330 here, you have to recognize a couple of things. The first thing is there's no pressure on the plugs. Because there's no pressure on the plugs, you don't get exactly the same thing that you excuse me, that you would normally see, but you get a pattern, and the numbers may be a little bit off. Okay, we've got 3.8 milliseconds of on time when we're looking for greater than 2.0. This is a very common pattern, and you can tell why it's pretty common. Look at what your high voltage is. High voltage is the wrong word. 4.8. It's a 5-volt signal, isn't it? So in other words, what we're doing is we're generating inside the PCM a 5-volt signal, and we run that signal, and when the ignition coil sees that 5-volt plus signal, it turns on primary current. And if we go down here to the bottom end, 0 volts. Wow, I got lucky. Usually you don't get quite that lucky. So using one cursor for voltage, you can get students to recognize, yeah, okay, that's coming from the PCM because it's 5 volt. It certainly didn't come from the battery, right? And the second thing is, how long was primary current on? Primary current stays on for that amount of time. One other thing, and then I'm going to pull the plug here, or I'm going to go back to my PowerPoint. When you do fuel pump speed with a pico is one of the greatest cheating tools around. Have the students do all the math, but what you're going to find, notice in the lower right hand corner, 15,759 RPM. Now this is not a signal that you should be determining RPM off of. But if these cursors were set from here to here on a fuel pump, that fuel pump is running 15,000 RPM. Pretty high. But anyway, I hope you picked up at least one thing that you can use tomorrow. My goal is always to give you something that you could use the very next day. My email, alsantini@consulab.com. And please keep ConsuLab in mind. Our goal is to help you teach technology. And I can't think of any better goal than that.
That concludes this session. Thanks a lot for watching. Now for a quick word from our sponsors.
Today I want to show you one of our exciting new products. It's the EM330-1 Fuel Injection and Engine Management Trainer. As an instructor teaching fuel injection and engine management classes, you've got your work cut out for you. You've got to go out in the shop, get the car, get it all set up, prepped, before you can do the demonstrations for your students. So what we've done at ConsuLab is we've designed a product to meet your needs. This product is designed around a steel frame, heavy-duty casters. It's only 30 inches wide. You can roll it right into your classroom and get set up in minutes. Now on the product, we have the full OBD2 diagnostic system. We have the engine control module and body control module. Then we have all the inputs for the engine control module. Now this system uses a drive-by-wire. So we have the accelerator pedal position sensor and pedal down underneath. On the top, we have the throttle actuator control motor. We also have the coolant temp, both oxygen sensors, NOx sensor, MAP sensor, as well as mass airflow sensor with the integrated intake air temperature sensor. Here we have the cam sensor and crank sensor, as well as the fuel injectors, the 4 ignition coils, as well as spark plugs. Down underneath, we have the fuel pump and fuel tank, as well as the filter and pressure regulator. Using a scan tool and the included OBD2 data link connector, we can access all of the data bits for all of these sensors, and we can also do bidirectional controls. What about the control panel? On the control panel, we have a breakout box with all the terminals from the engine control module. We have an ignition key. Then we have 4 variable sensors, so we can vary the intake air temp, the mass airflow, MAP, and coolant temp settings. Then we have a signal generator for the oxygen sensors. So what we can do is we can show a real live oxygen sensor reading, just like you would find on a car. Then we can create conditions where you have both a rich and lean situation with the oxygen sensor. So let's fire it up and see what happens. Here we see the drive-by-wire system in action. Notice the throttle plate's response to accelerator pedal movement. This product has been designed to make your job easier as a teacher. To find out more about our products, please visit ConsuLab.com, or you can follow us on Facebook, Twitter, or LinkedIn. Thanks for watching.